My name is Yerto. I'm the marketing engineer for Mega North America, and I'll be acting as the moderator for today's presentation. I will be supporting you on any technical issues or questions for our presenter during the session. On the right-hand side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions during the Q&A segments. You will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Jason Salchek, Application Engineer for Cable Products. Jason is based out of our Dallas office in Texas. Thank you for joining us, Jason.
Thank you for having me here. Just to start here, we're going to go over the scope of what we're going to cover in the webinar here. So we're going to cover basically our VLF withstand testing. That's going to be the bulk of it. Voltage levels, the test duration, the test standards that we're testing to. And we will also talk a little bit about monitored withstand testing. In addition to this, we'll talk about how to size a test set. Why do I need a certain size? What are the parameters that go in with that? And just as a nod to last month's webinar, we'll not cover partial discharge and 10 delta testing in depth here. We'll mention it a little bit, but we covered that in depth last month with our webinar from Henning Ochen, and that is available as a recording. So to get started, we'll talk, here's the agenda, talk a little bit about the cables and take a very high-level view of the why, when, and what of VLF. Talk very briefly about the historical backgrounds. We'll talk a little bit about the aging conditions, what we're actually trying to detect with our VLF testing, and then we'll spend a lot of time talking about modern withstand testing. So, as a review, just so we're all on the same page, we'll talk very briefly about the parts of a cable. We start, of course, with the conductor, the current carrying component. It's typically aluminum or copper, maybe stranded or solid. Following that is a thin layer of semiconductive material. This is often overlooked, but it serves a very important role. In cables that are particularly stranded cables, we have peaks and valleys in the outer radius of the cable, and they can create very severe voltage gradients. So this semiconductive layer helps smooth those out and provides a nice smooth transition into the bulk insulation. Of course, the bulk insulation is there to hold the voltage back. It's typically EPR, XLPE, although there are many other kinds of insulation out there. After the bulk insulation is another layer of that same semiconductive material to provide a nice smooth transition in voltage out of the bulk insulation and onto the metallic screen layer. Finally, we have another often overlooked layer of the outer jacket. Primarily, that's there for mechanical and moisture protection. So, what kind of cables are we going to talk about here? Most commonly, we'll see EPR, XLPE, or PILC type cables. EPR and XLPE we very often lump together in a term called extruded cables or solid dielectric cables. That's because the bulk insulation material is solid. The EPR maybe feels a bit like a pencil eraser. The XLPE feels a little bit more plasticky. The PILC cable we treat a little bit differently often because the insulation material is of a different nature. It's paper wrapped around the center conductor and then filled with oil. And the paper provides a structure to the cable, but the oil is actually providing the insulation qualities. These can come in single-phase or many different types of three-phase varieties. So, what do I mean by aging? All cables have some kind of life. Often you'll hear terms of 30, 40 years as an expected life of a cable. Things like thermal stress, electrical stress, mechanical stress, and environmental stress can all reduce the life expectancy of a cable. Thermal stress can come from overloading the cable, pushing too much current through it. Electrical stress can come from overvoltaging the cable, for example, or regions of high voltage stress. Mechanical stresses, they can come from nicks and scratches put in the jacket as the cable is being pulled in and installed. It can also come from overbending the cable, exceeding the bend radius of the cable. When the cable is then returned to being straight, sometimes you get air bubbles. The layers, the various layers in the cables will delaminate, and you'll get air bubbles, and that'll create a cable failure at that point. And environmental, typically wet conditions, do contribute to a reduced cable life. So why are we even testing here? Ultimately, the goal here is to increase the reliability of the system. We're reducing the number of unplanned outages, increasing our safety index, and we're able to proactively repair and replace questionable cables. We can do some preventative maintenance. We can ensure that there's no defects in manufacturing or workmanship. We can prevent the fault from even occurring in the first place. Or we can predict that the cable is about to fail by doing some preventative maintenance. We're trying to catch these aging conditions before we suffer an in-service fault. So when do we test? IEEE, and the standard here is 400.2, lists 3 occasions when we test. And that's the installation test. That's basically a delivery test, ensure there's no damage from shipping. There's an acceptance test. That's a test upon completion of work, so the cable's all done, but before we energize it. These would fall under the preventative maintenance. We're trying to pull out these faults before we energize the cable. And finally, we have our maintenance test schedule. This is somewhat reduced voltage level, and it's a regularly scheduled check of the cables, typically every 3 to 5 years. One that falls outside of the standard is that people do often is after repair test. There's no standard for this, but oftentimes it's about a 5-minute voltage pressure check just to make sure that the cable's not going to fail as soon as you put it back in service. So, from a very high level, what is VLF? Fundamentally, it's an AC overvoltage test or an AC high pot. It's performed at 0.1 hertz. So it's like a pressure test. We're going to apply a voltage above operating voltage, and those voltages are all listed in IEEE standard 400.2, and we're going to look for a breakdown. The cable will either survive the test, it'll pass the test and not break down, or it'll break down. So it's a simple pass-fail kind of result. This does provide us limited diagnostic information, but we can use VLF technologies. We can add some measurements and then do partial discharge diagnostics or tan delta diagnostics with the same basic waveform, with the same basic power supply. So, historically, or for many, many years, DC test sets were used. They were small, light, portable, inexpensive. It checked really all the boxes. But the cables at the time were laminated PILT cables. And because of the oil in the cables, they're different than the extruded cables. The extruded cables then will develop a trapped space charge. If there's any kind of imperfection in the insulation, a small speck of dirt, a small air void, anything along those lines, the electrons that are moving in one direction with the DC test, they'll gather at that imperfection. And that creates a region of high voltage stress, and that'll eventually cause a cable failure. We don't see this problem with PILT cables because the oil moves around and the electrons can't gather in one place. So, due to the trapped space charges, we find that the cables actually have a reduced life expectancy. And there's an EPRI report test number on the screen here if you want to look that up. Additionally, so DC Hertz are solid dielectric cables. It's also blind to certain defects in both kinds of cables, so both extruded cables and PILT cables. And what do I mean by blind to certain defects? These gentlemen published a paper here where they tested both AC and DC waveforms in a pretty severe fault. They drove a needle partway through the installation and grounded it. So it's not a complete short, but it's a pretty severe defect by anybody's definition. And what they found was that AC was 100% effective at finding this fault, and DC was 0%. And there's the numbers on the screen there. Not only was DC ineffective at finding this fault, DC was ineffective at finding it at much, much higher voltages, 8 and 10 times operating voltage, compared to AC finding it at about 3 times operating voltage. So VLF is much more effective at finding these faults at much lower voltages. And this is true for extruded cables, which is on the left here, and also PILC cables, which is on the right. The only difference in their test setup was that for the PILC cables, they drilled a hole and filled it with water. But it was the same ultimate results. DC was 0%, AC was 100%. And finally, there is no DC standard, or no IEEE standard for DC testing on extruded cables. IEEE 400.1 exists, which is DC guidelines for testing on laminated power cable systems. And they go out of their way to specify PILC, paper insulated, lead covered, pipe type, or in general, laminated cable systems. So at the moment, no standard or guide exists for, no IEEE standard exists for DC testing on extruded cables. So if we can't use DC, then what do we have to use? Well, the only alternative here is AC. And we can use 50 or 60 hertz power frequency, or we can use our 0.1 hertz VLF. In an ideal world, we would use 50 or 60 hertz. That's what the cable sees in real life. That's what it's would be the most realistic test. However, if we go to VLF frequencies, 0.1, we get a huge advantage in the power required to charge this cable. In fact, the difference between 60 hertz and 0.1 hertz is 600 times less power. This allows for practical field portable test sets. So I have some examples here with some numbers. Basically, the top one here is a 1,000-foot piece of 15 kV cable. If we tried to test it at 60 hertz, we need almost 10,000 watts or 10,000 volt amps to charge this cable. Compare that to VLF, where we need less than 20 volt amps or 20 watts. So we get a huge, huge advantage in power savings. And it's the difference between driving a truck to the cable or being able to pick up a piece of test equipment. The second example is a similar idea. It's just a longer piece of cable, and we see even more dramatic power savings. So the VLF values, they come from IEEE 400.2. It lists voltages for many voltage classes of cable from 5 kV up to 69 kV, and it breaks them up into the installation, acceptance, and maintenance test values. So with that in mind, how do we size a VLF unit? Well, of course, you have to get one that reaches the voltage required based on IEEE 400.2. That's a given. But in addition to that, we also have to make sure that our VLF test set is powerful enough to charge these cables. So even though it's much less power, 20 watts or 300 watts or so, depending on the size of the cable, we have to make sure that we can charge that. And the capacitance of the cable varies by conductor size, voltage class, and insulation material. In general, as a general trend, higher conductor sizes and a lower voltage class results in a higher capacitance per length. I have some example numbers here. It's impossible to give you a number for your cable because they're all a little bit different, but these are just some general numbers for XLPE type cables. And we can see here that as the conductor size increases, the capacitance increases, but as the voltage class increases, the capacitance per mile decreases.
Jason, before we move on, can we field a couple of questions from the audience? So Kushal wants to know that since the frequency is so low at 0.1 hertz, does it mean this is equivalent to a DC high-power test?
That's a great question. No, 0.1 hertz is very much an AC high-power. It's just very slow. We switch frequencies. We switch from a fully positive peak to a fully negative peak in 5 seconds. And it also, if you think about what the electrons are doing, they're getting pushed into and out of the insulation material every 5 seconds or 10 seconds, depending on your perspective of it. So no, there is an oscillation just like an AC voltage source.
Okay, let's move on. Oh, okay, there's another question came in. So when would you select VLF testing instead of DC high pot for medium voltage cables?
Basically, for medium voltage cables, the only time DC is still acceptable is for PILT cables. It's the only time IEEE has a standard for it. So if you're testing on EPR or XLPE, you really want to be using VLF. Other than that, maybe there's some practical considerations. You only have a DC test set available or something, but as far as standards go, you're really looking at VLF anymore.
Okay, maybe one last question because it involves the table that was just shown. So looking at the table on your previous slide, with voltage and cable size, what about the length of the cable?
Yeah, those numbers were given per mile. So if you have a longer cable, if you have 2 miles, you double them, or if you have a shorter cable, half mile, you cut them in half.
Okay, let's move on.
So what are we actually looking for here? What are the aging conditions we keep talking about? Primarily, what we're really talking about are water trees. Almost every cable will develop them. Some are more susceptible than others, and I know that the cable manufacturers have been hard at work developing better and better technologies to avoid this issue. We have two basic kinds of water trees that we'll be talking about. We can kind of classify them into two groups. In the lower left of the screen, we have small distributed water trees. These are an issue, but they're not necessarily a critical issue. On the lower right, we have one very large tree, and those are the ones that we're really concerned about. They're the ones that can cause us problems in the very short future here. So what happens with these water trees is that they disrupt the nice even field strengths that these cables are designed with. In a perfectly good cable, we have radially symmetric field strengths throughout the entire cable. But when the water tree starts to grow, it disrupts this field strength, and it can create a region at the tip of the water tree that's very, very high voltage stress. And if that voltage stress exceeds the capabilities of the insulation, then we form what's called an electrical tree. And we can see on this picture here a very visual difference between what a water tree and an electrical tree would look like. Water trees are pretty dense and generally straight. The electrical trees are much sparser and much more random in their paths. The other critical difference here is that water trees tend to be poor insulators. So if you can imagine that these cable manufacturers have spent a lot of time and energy developing the best insulation material they could, and if we introduce water into this, that can only make the insulation worse. So water trees are poor insulators compared to electrical trees, which are actually pretty good conductors. So there's a subtle but important difference there. And the conductivity of the electrical trees comes from the carbon paths that are deposited on the outer edges of the channel. Once the electrical tree bridges enough of the insulation, that cable faults, and now we have to go repair it. So water trees can come in many different shapes and sizes. We have some different examples here. We have some small ones distributed throughout the insulation, and those generally aren't a critical concern at the in day-to-day life. At the 9 o'clock position on the picture, we have a critical size water tree. This one has grown to the point where that voltage stress is so high that it's in danger of growing an electrical tree at any moment. And once that happens, the cable fails in a matter of hours or so. The water trees take a very long time to grow, 5, 10, 20 years, somewhere in that order. But electrical trees, once they form, they'll fail a cable in a number of hours. So when we talk about modern withstand testing, when we talk about VLF testing, what is it? What are the goals? What are the parameters that we're testing to? And what is actually happening during the test? So VLF testing is an AC voltage at 0.1 hertz. The voltage is going to be selected based on the IEEE standards, but it's going to be a voltage above rated voltage. And the idea here is to put pressure on the cable to find the weak spots. VLF testing is a check of the overall integrity of the cable system, and VLF testing in itself, just VLF withstand testing, results in a pass-fail test. Later on, we can add more diagnostic information from it, but in its basic form, VLF testing is a pass-fail test. And the goal of this testing is to detect local weak spots in the installation. And we find those weak spots by causing existing weak spots to fail during our test time. We cause them to fail during our scheduled test time. We've already scheduled this outage, and we fail them during controlled test conditions. So what do I mean by local issues? We can have local issues in terminations caused by workmanship. We can have global issues of these small distributed non-critical water trees. Those are really not the ones we're targeting. We can also have local issues in the joints or splices caused by workmanship issues typically, or possibly manufacturing defects. And we can also have critically sized water trees as a local issue in the overall cable length. So VLF testing then is for these local issues. We're really not targeting those distributed water trees. Those small ones are not an issue yet. We're going to wait until they grow to a critical size. So the goal of VLF testing then is to improve the reliability of the system by accelerating existing weak spots to failure during our scheduled outage, under controlled test conditions, and critically at reduced energy levels. So we just talked about VLF testing requires a few hundred watts at most. Compared to a in-service fault, the amount of energy that you would experience during a in-service fault is incredibly much less energy. So by using this reduced energy levels, we can limit collateral damage and therefore restoration time. We may be able to find a fault in a single phase during our test time that if it were to fail during in-service, it would have taken out all three phases and very much increased our repair time. We're also able to repair and replace these cables on a planned or proactive basis. Instead of being unplanned and reactive and responsive to faults, we can go out and choose the time that we want to find these problems. So I hear you guys saying faults. I don't want faults in my cable. Well, VLF accelerates the aging conditions of existing weak spots, and it causes them to fail during your testing time. Of course, choosing the time of your failure is much preferable to a random in-service failure. Everybody's well familiar, I think, with Murphy's Law, and if we let our random in-service failures just happen, chances are it's going to be at 2 a.m. on a Thursday in some rainy or snowy night. I would much prefer to have that fail during a nice sunny Tuesday morning. Additionally, VLF does not cause problems on the cable system. And there's a NETRAC report out there. There's a number on the screen here. And I've quoted some of their lines from it, some of their findings. I particularly like this last one here. It seems reasonable to conclude that the current levels of voltage and time recommended by IEEE Standard 400.2 are reasonable at finding defects in a wide range of utility cable systems and do not pose an unreasonably high failure risk for cable systems either during tests or afterwards. Basically, they age cables for a number of simulated years. They have their methods for aging cables. And when they did the VLF test, they found no correlation with cables that had been VLF tested versus those that hadn't in the number of faults. So VLF testing does not put faults on cable, but what it does is cause them to fail at a more convenient time for you, and therefore avoiding unplanned outages. So what do we mean by critical trees? In almost all cable systems, there's going to be some small, non-threatening trees. The exception might be newer cable systems. 5 and 10 years old may not have this, but the age systems typically do find some amount of treeing. There's also some imaginary point in there that's a critical point, and I represented it here by a blue line. When these trees grow, past this critical point, they're in danger of failing in service. They can fail at any time. They can create this electrical tree and cause a failure at any moment. What we do at VLF testing then is we push this critical point out. We put it deeper into the installation so that we can find these medium-sized water trees, these ones that are going to grow to failure in the next couple of years, and we can cause them to fail during our test time. If this larger one at the 9 o'clock position hadn't failed yet, of course we'll find that one. But also this one that's not critical yet, it'll cross a critical line in a year or two. We can cause that to fail during our scheduled test time when we have people and material available to us to fix this. And we're not targeting these small water trees. These smaller ones are very likely, based on the rate of growth, they're very likely to be okay until the next scheduled test. And VLF does not cause those to grow at all. This is the symmetrical process. Water trees grow from the outside in just as much as they grow from the inside out. So there is a critical point on the outer side as well. And for example, there's a picture of a water tree that's growing from the inside out that's in danger of failing in service. So what happens here? What are the results? Well, the cable can pass. It can hold the prescribed voltage for the required time without breakdown. And based on a report from Dortmund, which is a city in Germany, and their 20 years of experience with VLF testing, if a cable passes VLF testing, statistically it's about 97% reliable for over 2 years. So they find 97% of their faults for the next 2 years during their test time. If the cable doesn't pass, well then it breaks down, and we now have a faulted cable, and we have to repair it or bypass it. And with that in mind, we should have on standby some CFL equipment, spare cable, splice kits, things like that, or backup cable, some alternative plan to keep customers in service while we repair this cable. So that's what we're trying to do with this VLF testing. Then we'll get into the parameters of the tests and what we're looking at with these. So we have 4 parameters here: frequency, voltage, waveform, and test time. The frequency and waveform, that's typically dictated by the equipment you get. They're going to be 0.1 hertz and either sinusoidal or cosine rectangular pieces of equipment. So that's a decision you make once, and then that's it. The voltage level and test time, that's the kind of information that you need to know at the time of the test. And it's going to be based on where the cable is in its lifespan. So, frequency, if you're testing the IEC standards, it only recognizes 0.1 hertz. If you're testing the IEEE standards, they highly, highly recommend 0.1 hertz. However, they do allow you to use lower frequencies. That would be done, we talked about the capacitance of the cable. If the cable capacitance is too high for your VLF test set to charge, IEEE gives you a way to reduce the frequency and increase the testable capacity of your test set. However, IEEE recommends that if the frequency is lowered, the testing time should be increased. For example, if we go from 0.1 hertz to 0.01 hertz, a factor of 10, we go from a 1-hour test to a 10-hour test, or similarly for other factors like that. They do caution that results at lower frequency may not result in the same results. They may not be comparable because of a lower dV/dt or change in voltage over time. You wind up with significantly less stress, and there's a little bit less data to compare to. And there's a quote from the IEEE standard just to that effect. So 0.1 hertz is the frequency, and now we can choose either sinusoidal or cosine rectangular. Both are recognized by IEEE, and they have charts for both waveforms. So I think most commonly sinusoidal waveforms are widely available, and we also use the sinusoidal waveform for tan delta testing. Everybody's familiar with a sinusoidal wave. It's a nice smooth transition, positive to negative, and nice smooth voltage transition. This other waveform, this cosine rectangular, is a little bit less common, but but cosine rectangular units tend to have a higher testing capacity, size for size. We cannot use it for tan delta testing, but because of the nature of the wave and how fast it switches from positive to negative polarity, it results in a higher change in voltage over time, results in a higher voltage stress, and it gives us a better reading in partial discharge. It also tends to cause these defects, these latent defects in the cable, the ones that we're targeting, it tends to cause those to fail quicker. So, a little bit of a zoom in here on the cosine rectangular. It is a 0.1 hertz VLF frequency, but at the transition from the positive to the negative periods, we shape the waveform in such a way to mimic power frequency. So based on the capacitance of the cable, that can switch in about 8 to 10 milliseconds or so. Very similar to the change in polarity of 50 or 60 hertz power frequency testing. So it's VLF testing. We get the benefits of the lower power consumption, but we also keep the benefits of power frequency testing in the fast voltage transition there. So those are the types of things, the frequency and the voltage shape, that we tend to make at the time of purchasing the VLF test set. When we're actually at the cable, we have to decide what voltage level we'll test to and for how long. So IEEE has 3 voltage levels, depending on where it is in its life. The installation test, and that's basically a delivery check. When the truck pulls up, this can be done with the cables on the reel still. Truck pulls up, you're just looking for damage during shipping or from the manufacturer. More than once now, trading stories with different customers, I've heard where a truck driver would staple the bill of lading right directly to the cable, and they have 2 little fang marks in there that are going to cause you trouble down the line, but a VLF installation test is very likely to detect something like that. For acceptance testing, many times, not always, but many times people do skip the installation test. It's because the acceptance test should always follow that. The acceptance test is a higher voltage than the installation test, and it's performed when all the work is done on the cable. All the splices are done, all the terminations are done. The cable's still isolated from the rest of the switchgear, but otherwise the work on the cable is complete. And what we're looking for here is still any transportation or manufacturer defects, but primarily workmanship issues in joints and terminations. And this will be, or should be, the highest voltage level this cable ever sees in its entire life. If you look on the next column here is the maintenance test, and that's typically on about 70 to 80% of the acceptance test. And we do the maintenance tests when the cable's already in service, and instead of looking for workmanship issues, we're now looking for aging conditions. You know, obviously, it's a brand new piece of cable. There's not going to be any aging conditions on it. But as the cable ages, those water trees grow, and that's what we're looking for. And this is the lowest voltage level of the pressure tests. So a little bit closer look at a segment of the IEEE 400.2 table, and it's table 3. It's very easy to read. It's a matter of selecting the waveform that you're going to be using, and that's dictated by your equipment again. Once you select the waveform, you select the voltage rating of your system. In this case, let's take an example of a sinusoidal 5 kV cable. And then you decide if you're doing the installation test, the acceptance test, or the maintenance test. So if you're done putting the splices and terminations on but haven't yet put this cable in service, you're going to do an acceptance test. If the cable's been in service for a number of years, you're doing the maintenance test. And in general, the maintenance test values are about 70 to 80% of the acceptance test values. But IEEE has this chart everywhere from 5 kV to 69 kV.
Oh, okay. Before we move on again, a couple of quick questions from the audience. At what cable age should we start implementing VLF testing?
Very good question. There are some standards out there. I believe NETA and some of the manufacturer standards recognize DC testing up until about 5 years of the cable's life. After that, I'm not aware of any DC test standards. However, there's at no time in the cable's life can you not use VLF. To say that another way, you can use VLF the entire life of the cable compared to the limit of 5 years on DC testing. If you're asking when it goes from a new installation to a or goes from an acceptance test value to a maintenance test value, typically you do the maintenance tests and put the cable in service and you don't come out and touch it again. If you're out there and things are failing on you, well, that's an abnormal condition and you have to make that determination. But after 3 to 5 years, you're going to start looking at the maintenance test values exclusively.
Okay, and is there any difference between a 50, 60 hertz withstand test and the VLF test in terms of accelerating aging conditions?
Yes, there is. At the voltage levels we're talking about 2 times operating voltage for the maintenance test values, it turns out that 50, 60 hertz is actually very similar in terms of growing the water trees, growing the electrical trees. It's very similar to VLF. As you vary that in voltage, if you go less than that or more than that, there becomes a little bit of a difference. But at our target voltages, they're actually very similar.
Okay, and the last question, if you compare VLF testing with DC high-pot testing, is it still considered a destructive test?
So, yeah, it's an overvoltage test. I know NITA has their has the explanations of type 1 and type 2 and destructive, non-destructive. I want to be very careful with how I use the word destructive. VLF does not put problems on your cable based on NETREC research and things like that. But if there are problems on the cable, it will cause your cable to fail, and that's the goal of VLF testing. That's what it's designed to do. So in that sense, it is destructive, but only if there's a problem on the cable. It's not going to cause additional problems.
Okay, let's move on.
So we just decided on what type of test we're doing, whether we're installation testing, acceptance testing, or maintenance testing. And the final thing we have to decide on here is test time. So based on the IEEE standard, they recommend 30 to 60-minute tests. Based on the 20 years of experience from this Dortmund report, they find about 75% of their faults on age cables. They find about 75% of their defects in the first 30 minutes. But if they extend it out to the second 30 minutes, they find 25% of their faults. So for age cables, it's often a very good idea to run for the full 60 minutes because these aging conditions, these water trees and these electrical trees, they take some time to grow. It doesn't happen instantaneously. First you have to grow the water tree a little bit, then it has to convert over to an electrical tree, and then that electrical tree has to grow through the insulation. So it takes a little bit of time, and the very, very worst thing we can do is start this process and then abort the test early or stop the test early and put this cable back into service. That will result in an in-service fault, and that's exactly the thing we're trying to avoid. So it's a very good idea then to run these tests for a minimum of 30 minutes, and if we want to get the last 25% of our faults, get that last little bit of reliability, we're already there, we're already switched out, we can run it for another 30 minutes to bring the test time up to 60 minutes. This is specific to age cables for your maintenance test values. For acceptance testing, typically you do see things fail a little bit quicker, so 30-minute tests are often enough, but there's no harm done to the cable by running an acceptance test for 60 minutes either. So that pretty much covers the VLF withstand testing, basic withstand. It's simply a pass-fail test, go, no-go test, and it very much is the modern equivalent of a DC high-pot. Talk a little bit here about monitored withstand testing. What that is a combination test. We take the parameters from the withstand test, so the frequency, the waveform, the voltage level, and the time, they all stay exactly the same. but what we do is add the measurements from tan delta. And a report might look like this, where we have this sinusoidal wave, and then at every cycle, we take a tan delta reading. And what that does is it allows us to monitor what's happening with the withstand test. It's more than a go, no-go test. We're able to get signs of failure from these increasing tan delta readings. Very similar to running a DC high pot and watching for increasing leakage current. We can run this monitored VLF withstand test and watch for increasing tan delta tests. There's no standard for this, but if we're able to start seeing these tan delta readings off, we are able to abort the test before the cable fails. At this point, we have to make a decision. We may be able to return this cable to service for a short time, but at an increased risk of failure. We know that this cable has not passed the test. We know that this cable is not good. So why would I choose to do this? Well, maybe I don't have materials available, or I ran out of splice kits or something along those lines. That would be a good reason for why I would abort the test. We can do the test, come back and cause this cable to finish this test at a more convenient time, or when I've arranged for materials or personnel or cable fault equipment to be available. So, in summary then, basic VLF withstand test just gathers basic information about the cables. It's able to weed out bad cables and also able to weed out weak spots by growing these electrical trees to failure. What it cannot tell you, though, is how well the cable is. Did it just barely pass the test, or is it very strong and pass the test very easily? It can't tell you if the cable is experiencing high losses, which is a sign of aging on the cable, or if there's a significant amount of water trees in there. Additionally, it doesn't localize the defects. The only way to find these weak spots is to cause the cable to fail and then use our cable fault equipment. So if the withstand test doesn't provide the information on the installation condition, what are the alternatives? What tests do I need to run? And that's when we're going to talk about the diagnostic tests, tan delta and partial discharge diagnostics. And tan delta is good at global assessments, looking at the overall condition of the cable installation. Partial discharge is good at looking at local issues, problems in splices and terminations typically. So I'll again point you towards the webinar from last month from Henning Ochen. It should be recorded and available for everybody to look, and that's where we got into some of these diagnostic questions. So thank you very much for your time, and I think we have some questions.